We're going to be looking at the Doppler effect today, and there's two aspects to it. We're going to be looking at a qualitative understanding of the Doppler effect and then a formula. And I firmly believe that you cannot be really good at calculating unless you understand what's going on. Okay? In other words, we have to talk about the qualitative thing first before we talk about the quantitative thing. The Doppler effect is used to explain why waves can deceive you into believing they have different frequencies than they really do. Okay? If the source of a wave is moving, the frequency that you observe is different than if the wave were not moving, the source of the wave were not moving. Okay. So this diagram is showing a source of a wave, and that wave is dropping ripples in maybe a water tank regularly. So these are circular ripples that are traveling outwards at some constant speed. And what happens here is if you were here, this is O for the observer and this is S for the sound wave. If you were here, these ripples in the wave, these compressions is really what they are passing your eardrum regularly. Capiche? So if that source of a sound wave or a water wave, I guess we'll go with a sound wave, is dropping compressions at a rate of 500 hertz, then these compressions are going to be passing by you 500 times per second, and your brain picks that up as 500 hertz. If the source of the wave is in motion, then the wavelength produced in front of the source will be different than the wavelength produced behind the source. Below is the same source of sound waves as in the above diagram, but the source is now moving to the right. So I have three things going on here. I have a source creating a sound wave, and it's moving, but I have an observer behind the source, and I have an observer in front of the source. Can somebody explain to me why, and you can default back to water waves if you like, why are the ripples or the compressions closer together in front of the source? Yep.
Well, isn't that the direction that it would be moving?
True, but why are the ripples or the compressions going to be closer together? Which, by the way, you can make a note here that this is a smaller wavelength, and back here there is a bigger wavelength. Yeah.
Since it's moving in that direction, then it's kind of chasing the waves.
That's a good way to put it. It's kind of chasing the waves. It's catching up in a little bit. It's not really catching up, I guess. I shouldn't have said that. But it's moving in the same direction as the waves, which is what you said, but now we're going to add something more, which was what Colin said, is it's moving behind the waves and it's chasing it. So one way to look at it is, if I am that source, and maybe the wave that I'm creating is I'm in a boat and I'm just tapping the water with an oar regularly, then I tap the water once, that ripple moves towards the right. I tap it again, a second ripple moves towards the right. But if I start moving the boat towards the right, when I tap that water the first time, I create a ripple that's traveling to the right, but I'm chasing it. It's a really good way to put it. I'm behind the wave, getting closer in that direction. And then when I tap it again, I will be creating a second ripple that will be closer to the first ripple than if I tapped it without moving. Okay. On the other hand, on the other side, when I tap the water and then I move to the right, that ripple is traveling to the left. By the time I tap the water a second time, it has moved quite a fair distance. So my second ripple will be even further apart. And the result here is that you are going to hear a higher frequency here because the ripples are going to be passing my ear quicker. Not quicker, more frequently. The frequency with which they'll pass my ear will increase. Whereas over here, you hear a frequency that's lower. this is why, and I really didn't know this until I took physics, if you're at a train crossing and you hear the train coming and it's blowing the whistle, it has a different sound when it passes you. And I thought they were just using a different horn. When they're coming towards you, it has a higher sound, and then as soon as they pass, it drops. It may be perceived as a drop in volume, but if you listen to it carefully, you will hear a different frequency. So I'm going to demonstrate that to you with this very annoying sound. Okay? And I suppose what I could do is I could get us all out in the hall and do this and run towards you. And then I could run away from you. I don't really feel like running today. So what I'm going to do is I'm going to swing this in a horizontal circle, and at some point the thing is going to be moving towards you, and at a different point it's going to be moving away from you. Keep in mind, you're all in different places. So when Gabrielle hears it higher pitched because it's going closer towards her, Sam might hear it not quite as high a pitch because it hasn't gotten to that part of the orbit yet. So I'm going to go over here because I want to swing this in an orbit that's about 1.5 meters long. Wish me luck. Now, I don't hear any difference, really. Do you? So when it's moving this way, it's higher. When it's moving this way, it's lower, yes? Okay. Enough of that nonsense. You're going to get an equation here shortly that we will use together to solve some problems, but I would like you to understand something else. That this is going to be what happens. You need to understand that if these two things, the source and the observer, are getting closer together, the observer will hear a higher frequency, which means the wavelength will be shorter. Okay. However, I hope you understand that rather than me swinging that thing around, I could keep it stationary, and if you were on a merry-go-round moving in a circle, when you're moving towards the source, you're going to be passing the ripples more frequently than if you're not moving at all, right? If I go back to this diagram, if the source moves towards me, these compressions get closer together, so they're going to pass me more frequently. I hear a higher frequency. If I, the observer, move this way, these ripples are not actually getting closer together, are they? But they're going to be passing my eardrum more frequently. So I will still perceive a greater frequency. In other words, and this becomes crucial in a few minutes, if the two things are getting closer together, the frequency goes up. If the two things are getting farther apart, the frequency goes down. So, describe the wavelengths and frequencies on both sides. Well, we can kind of, it's in the diagram, but the bottom line is the frequency increases when the source and the observer get closer together or approach each other. And I always just write the frequency, but I think it's important for you to understand this is the perceived frequency. The frequency is the frequency. If I have that app on my phone that reads the frequency, and I'm on the train while the train is blowing the whistle, or the horn, or whatever you want to call it, it's going to read us the same frequency all the time. The frequency of that sound wave is what it is. It's a perceived frequency that changes. And by the way, this means the wavelength is smaller. Why? Well, because the universal wave equation says V equals F lambda. And the wave travels at whatever speed the temperature of the air gives it. It's the medium that determines the speed. So if the frequency perceived increases, then the wavelength observed must be less. We don't like to talk about the wavelength, though, because it's frequency that we experience. When you have a sound wave go by you and detected by your eardrum, you don't go, oh, yeah, I sense a certain wavelength. You hear a frequency. And the opposite is true. The frequency will decrease when S and O move away from each other. So this is, again, why a sound of a horn or a whistle sounds different when it's coming towards you than when it's moving away from you. If we had a little bit longer class, I'd go out to my truck. I'd get you all outside, bundled up. I would drive as fast as I can through the school zone without speeding, laying on my horn. And I've done that in the past. And you can really notice the difference. It's an experiment you can try on your own someday, okay? Here's the formula for the Doppler effect. Now, don't be intimidated by this. Let's break it down. This is the formula that appears on your formula sheet. So go to your formula sheet, too. Let's take a look at your formula sheet. I'll pull mine up. Oops. It's under waves. There it is at the bottom. Any formula now on your formula sheet that we have not learned about will be a Physics 30 concept or application. So there's a lot under waves here dealing with light. This has to do with mirrors and lenses. This has to do with mirrors and lenses. This has to do with refraction. This formula down here and the one below it have to do with interference, which is when I shone that laser through that piece of glass and you saw the dots. But here's the Doppler effect. So, what do all of these variables stand for? V is the speed of the wave. It's got nothing to do with how fast the train is moving. It has everything to do with how fast the sound travels through the air. That's it. F is the frequency of the observed wave. So this is what you hear. Well, I want to be careful here. This is what you hear if you're the observer. If you're the engineer on the train, that's not what you, well, that is what you hear as well. But we'll get to that. So V appears in a couple places here. And then the other two, F sub S and V sub S, are the source. So when we say the frequency of the source, we mean the frequency of the sound. We mean that if you stood right beside that sound source and measured the frequency with an app on a phone, that's the frequency of the source. And Vs is the speed that the source is moving at. You will notice something, though, that in this equation does not account for the observer moving. There's no place in this formula that says V of the observer. Okay? But we are going to solve problems where you are moving. And we'll get to that in a second. The weird thing about this formula is there's a plus or a minus. Okay? So sometimes everybody, you're going to use this formula, and sometimes you're going to use this formula. Sometimes you'll have to go V minus Vs, sometimes you'll have to go V plus Vs. So let me explain to you how your textbook and most textbooks would explain this to you. They would give you a rule. They would say that Vs, you're going to use plus if the source is moving away from the receiver. So your formula says the frequency you observe is V over V plus Vs times the frequency if you are moving just a second here. Yep. Away. I'm just breaking this down for you. I'm not going to use the rule, and I'm going to try to get you not to use the rule. There's a better way to understand what's going on. Let me ask you a question here. This is an S. Forget about the formula. When you're moving away, when the two things are getting further away, is the frequency greater or less? If we look at this diagram here, in terms of the observer, we're looking on the left, and these two things are moving away from each other. So the ripples get stretched out. The compressions get stretched out, which is a lower frequency, right? So this is less frequency that you observe. Now let's do the other one, and then I'll tie this all together. If the object or the source are moving towards each other, then it's saying you use a negative Vs. So this is moving together. Right? When you are moving closer to the source, or the source is moving closer to you, does the frequency go up or down? Goes up. So this is more. Okay. Well, I don't use this rule because I just say if the frequency is going to be greater, the bottom of this fraction has to be smaller to calculate a larger frequency. So how am I going to get a smaller denominator? I'm going to subtract that motion. And we'll see in a little bit that it doesn't just have to be the source. It could be the source or the observer that you're subtracting that motion on the bottom. When I look at moving away, I know the frequency has to be less. Because I think of it this way. If I have a wave that's being stretched apart, the ripples are further apart or the compressions are further apart, which means the wavelength is greater, the frequency is smaller. So I say to myself, how can I get this thing multiplied by the frequency of the source, how can I get it to be smaller? The answer is the bottom of this fraction has to be bigger. Do you catch my drift there? I think that's a more reasonable way to do it because then you're understanding what's going on. You're not just memorizing something. So let's take a look at a couple of examples. A car is traveling towards a stationary source sound. The frequency of the sound is 625 hertz. That's the frequency of the source. And right away, everybody, you'll notice the source is not moving. It's the observer that's moving this time. Read this question carefully. A car is traveling towards the sound. What will you hear in the car? So if I go back to this, it's the source that's stationary and the observer is moving towards it. It's different. It's different. But want to be very careful in explaining this. I want it to come out right. If I have a sound, a source, and the observer is here, and this is 625 hertz, and the observer is moving towards the source, will the frequency the observer hears be greater or less? Up or down? Up. Be greater. You'll hear more than 625 hertz, right? Here's my point, though. What you hear when you're moving towards the source at 29 meters per second will be the same as what you would hear if you weren't moving and the source was. And when I took physics in university and we learned about the Doppler effect, let me write down the formula here. It's frequency equals V, and by the way, I don't memorize this formula, I reason it out, okay? Over V plus or minus Vs times the original frequency. Right? And I know it's minus because the frequency has to go up because they're getting closer together, so the bottom has to be a smaller number. You with me on that logic? Okay. When I was taught the Doppler formula, it was this. R for relative velocity. It doesn't matter which one is moving, it's the relative velocity. So we're going to simply, even though this is source, we're going to use the velocity of the observer because it's the one moving. I'm going to go one step further, and I don't know if we'll get to an example like this today, but and don't write this down because it's not the question. If this were moving at 29 meters per second, and this were moving at 10 meters per second, then you would put 39 down here because they're getting closer together at 39 meters per second. If this is what's happening, the car is moving, the source is moving 10 meters per second to the left, and the source is on the right of it moving at 29 meters per second, are they getting closer together? Yes, so it'd still be minus. At what rate? 19, right? If, I want to make things interesting, and we're going to get back to the question in a second, if this were the situation, and it's not, then you would hear a lower frequency because you're getting away from the source. So this would become plus, and you would put 19 in there. This remembering when you use plus and when you use minus and limiting yourself to the source moving is not very helpful in the real world. Did I clone that page? I did. So let's get back to the business at hand here, which is that. And this is moving at 29 meters per second. Don't forget, this is the original scenario, but mathematically and physically, there's no difference between these two. So that's why we can put the velocity of the observer or the velocity of the source. So we put in the numbers. What the observer hears will be I've forgotten by now, 337 over 337 minus 29, and you multiply that quantity by 625. All right? You don't need to hit equals. Oh, that's not right. You don't need to hit equals after you enter this. I just like to do it. So what's happened, I like to do it to explain to students that what you're going to hear is a frequency that's 9% greater. It's going to be 109% of what it was. Is it 625? Okay, thank you. So about 683. We okay with that? The car in the first example, we're traveling away from the stationary sound. I feel that I've done a half-decent job in explaining why it was minus in the previous one, that I can just say to you here, are you okay with me putting R for relative? Because, I mean, I could do this. I could say, this is the formula on your formula sheet. But the source moving and the observer stationary is the same as the observer moving and the source stationary. It's the relative motion. So this is going to be the speed of the sound in the air over the speed of the sound in the air plus the 29 meters per second times the frequency of 625. Thank you for that, Gabrielle, and everybody else. Times, I'll just go times this time. So you're getting 575. Boy, what a fluke that it was really close anyway. Okay, so about 575 hertz. Just a little detour here before we move on and finish the lesson with the examples. How many of you have heard of red shift and blue shift in regards to stars and galaxies and planets? When something is red shifted, red light has a longer wavelength. So if it's red shifted, something is moving away from you. There's a way for you to look at the light from a star and tell what color the light is there. There's a way to do it. You learn about it in Physics 30. It's called spectroscopy. Because certain atoms emit certain colors of light, there's a way to identify the colors that you should be observing when you observe a star through a telescope. But when you do observe the light coming from a star through a telescope, you discover that the wavelengths of the light are shifted in the red direction. They should be this tinge of red, but they have a different tinge of red, which is a longer wavelength. And from that, you can figure out how quickly the star is moving. And most of the stars in the observable universe are red shifted, which means they are moving away from you, which is evidence that the universe is expanding. You may get some stars which are blue shifted, which means they're moving towards you, but that's only because they're in a galactic cluster of stars that's spinning. And some of them might be moving towards you, relatively speaking. Let's try the second question. A whistle with a frequency of 965 hertz is moving with a particular speed towards an observer, and you're given the speed of sound. What is the apparent frequency of the sound as heard by the observer? So, it's going to be the speed of the sound over the speed of the sound plus or minus the speed that the source is moving at, or the relative speed that the two things are getting closer together or further away from each other at, times the frequency. The question I have for you is, are we going to put plus or minus here? And if the whistle is moving towards the observer, the frequency you hear should go up, which means we have to subtract in the denominator to get a smaller denominator to get a larger number on the top. I think most students will be more successful reasoning it out rather than saying, oh, plus when it's moving, I can't even think of it, rather than memorizing those rules. So I want you to run that through your calculator, please. I'll do the same thing, 342 over 342 minus 23 multiplied by 965. I get a larger frequency. I mean, I suppose if you can't handle the math of what's going on with that denominator, you could try plus, you could try minus, and then pick the answer that gives you the right thing, which is a larger frequency. So this is about 1,035 hertz is what you would hear. Starting to catch on to this? Okay. And finally, if it were moving in the opposite direction, well, the only thing that would change is this would be a plus. Pretty basic. So you would have 342 over 342 plus 23 times the 965. Did I get all my numbers right this time? Okay. About 904. So that's the Doppler effect. Pretty straightforward.